So now that we've gone through a lot of the main processing steps, how we physically construct transistors and the metal layers that connect the transistors together, let's go through what are called the layout design rules. You've already encountered this a little bit as in the labs. The design rules are you specify constraints so that the patterns that we're putting on the wafer will actually conform to the desired topology geometry of the design. What I mean by that is basically you want a metal wire to be a certain width, and you want the distance between that metal wire to be a certain space to the next metal wire. You have to make sure that what you want to happen actually can happen on the wafer. So you have to create rules that allow you to pattern things on the wafer that are physically possible for you to do based on the design technology that you have. So the thing to keep in mind with design rules is typically the design rules that are given are not a 100% boundary between if you follow this design rule, you're guaranteed 100% that you'll be successful in putting that pattern on the wafer. And if you don't follow this particular design rule, you're guaranteed 100% to fail. Typically there's a, it's kind of a boundary between, as long as you follow these design rules, you're most likely going to succeed, and if you start violating the design rules, you're going to increase your chance of failing to generate the pattern you want. So there's a certain tolerance between probability of getting what you want on the wafer correctly. So potentially a layout that violates your design rules could still function perfectly well, depending on how much you're violating the design rule and what type of rule you're violating. And possibly also a layout that is correct to all design rules could still potentially fail functionally. And that might be a matter of like a design rule that wasn't known before you started. You created a new pattern that wasn't predicted and caused some sort of failure because of that. So the main thing that I want to reiterate here is if you depart significantly from your design rules, you're more likely to result in failures and not actually getting what you want on your silicon wafer. While talking about design rules, I should also mention basically the design rules are designed to make sure you can generate the masks that you need and then pattern those patterns onto your wafer using your photolithography steps as you desire. So one quick comment about the masks, the photo masks that will get generated, is that your mask layers that you'll wind up generating in order to generate the photo masks are not necessarily the same as what you're drawing when you draw your layout layers. So below in the figure, it's showing basically the mask layers that will get generated are what's shown in A, whereas in the B part of the figure is the actual layers that you draw in order to for your layout. So you can see here that in your layout you might draw an N-well, a N-diffusion, P-diffusion, and a poly layer. So you're drawing 4 layers, whereas the actual masks that will get created are you'll create an N-well mask, but instead of creating N-diffusion and P-diffusion mask layers, you'll generate an active layer and then a P-select layer and an N-select layer. And so there's not always a one-to-one correspondence with what you're drawing in your layout tool and the mask layers that get generated. So Like your transistor gate logically is the ANDing of your active layer and your poly layer. Your transistor source drain region is logically the ANDing of your active layer and not poly layer. Your P well is logically not your N well in this particular case. And your well contact is logically the AND of active and N select and N well. Your substrate contact is logically your ANDing of your active and your P select and not N well. So this is just going over one quote unquote relatively simple example of how mask layers actually get created relative to your drawn layers that you'll be doing in your layout tool. So I'm not going to go through all of them, but just keep in mind that there's not necessarily a one-to-one correspondence between your drawn layers and the masks that get created. And if you really want to know more, you pretty much have to talk to the process technology people in order to know what actual mask layers get created. So below I have listed some of the most important design rules related to wells and transistor design rules. So just kind of going through these quickly. First if you have your poly going over a gate region, the polysilicon has to overlap the active by a certain amount. You can't just end the polysilicon right at the edge of active. You need it to go beyond the active to make sure that if there's any misalignment between your poly and your active region, that you won't have your gate kind of ending before it needs to. It has to go all the way across the gate of the active. So polygate has to overlap the active and extend beyond it by a certain amount. And then if you have polysilicon in your field areas where it's not running over active, it actually has to be spaced away from the active by at least a certain amount. And so that's a different distance between field poly has to be spaced away from the active by a certain amount. Your N well has to overlap your N active. You need to make sure that your N plus active region isn't too close to the edge of the N well, otherwise any misalignment there might cause problems with your N active not being inside the N well. A similar thing, N well has to overlap your P active, and for similar reasons you want to make sure your P active is fully inside your N well, so any misalignment causes your P actives to still stay inside your N well. Any N well, N active that's outside of the N well, you don't want those to short together, so you have to have your N well spaced apart from N active that's outside by a certain distance. Similar thing, P active outside of N well has to have a certain space. The distance between P active and N well might be different than N active and N well. So they could be the same value, they could be two separate values. Any contact, so if you have a well contact inside your N well, you need spacing between that well contact, which is N active to your N well, needs to be spaced away from any P active, because you don't want those too close together, and to have the highly doped N and P that will have a much higher doping concentration, reverse bias PN region with really high doping concentration will also have a lower breakdown voltage, and so that's a problem. So you don't want those spaced too closely together. Any substrate contact has to be spaced out from your N active. Then of course your well itself has to have a certain minimum width. You can't have your well too narrow. Poly has a minimum width. Active has a minimum width. and your active has to be spaced from other active by a minimum amount. So those are just some of the design rules. They're the more basic design rules that you pretty much always have, but there's a lot of additional design rules on top of these. But be aware of at least these minimum design rules. So in addition to your well and active rules, there's a lot of additional design rules. I'll go through a few here on this foil. So some of the basic design rules that you'll see in pretty much all processes are well-to-well spacing for wells that are a different potential. So if you have wells that are set to the same potential, they might not need to be spaced out, but if you have wells in different potentials, you don't want them shorting together, so you need space between them. You might have a different spacing for well-to-well spacing if they're the same potential, because the reverse bias PN junctions will, if it's the same potential, might be different, so you might have different spacing for different types of wells. P-active spacing to N-active. Poly to poly spacing over active might be different than poly to poly spacing over field oxide regions. Your active extension beyond the poly, the poly has to extend beyond the active as it's crossing the active, but then the active, you can't have it stub out on, it needs to extend beyond the poly as well. So then making contacts to your actual silicon source and drain regions. Generally the contacts have like an exact width that they need to be. It's not just a minimum width. Generally contacts are a very specific exact size. The contact will need to overlap your, in some cases overlap the poly active metal regions. You have spacing between contacts, spacing between where you can make a contact and the gate. So if you're making a contact to your source drain regions, you'll need a certain space away from the gate in order to make the contact to the source drain region. Your via widths, if you're making, so contact is usually referring to the metal contact to the silicon. Vias is usually talking about metal to metal. So when you're going from one metal layer to the next metal layer, those are called vias, whereas metal to silicon is called contacts. So vias will have, again, generally an exact width dimension to them that's specified by the process and which via layer it is, and then you'll have certain spacing requirements for via to via space. The via generally needs to be overlapped by the metal by a certain amount. So how much overlap is a design rule, and then metal to metal. So those are generally some basic rules that are in all process technologies. In modern process technologies, you might have some additional rules, like your poly width. Instead of, in the basic rules, your poly might have a minimum width, but you can have a wider poly than normal. In some of the more modern process technologies, the poly width might have a maximum amount that it can be as well, or it might need to be exactly a certain poly width. In the really latest process technologies, you have one poly width, and that's the only poly width you use everywhere. One poly direction, and that's the same direction you use everywhere. You don't have bidirectional poly. Sometimes your active width might have a certain maximum active width that you can have, or it might need to be an exact active width. Like you can only have one width of your active, and it's the same width that you use everywhere, for example. With metal widths, you might run into something where you can have, again, a maximum metal width. You're not allowed to have, let's say you can have your minimum metal width, and then you can have, maybe at maximum you can go up to 3x width or 4x width. but you might not be able to go more than that. And in some cases, same thing for metal space. You might have a minimum space, but then also a maximum space between neighboring metals. Similar thing for vias. For vias, in some cases you might have a requirement for a via on a certain layer and then the via on the next layer above it. So via between metal 1 and metal 2, and then you have a via between metal 2 and metal 3. You might not be allowed to have those too close to each other, and there's various different process regions for that, or reasons for that. In some cases it has to do with just you can't get planarization. Your chemical mechanical polish maybe isn't quite good enough, and so you have some irregularities where the vias, existing vias are, and so you need to space out the via to the next layer by a little bit of a distance, so that there's not going to be problems due to planarization. Sometimes there can be issues with corners of active and metal layers, where instead of just a space to space for the straight lines, a corner to corner might be a different rule than a line to line. So as just the thing to keep in mind is, as modern process technologies have been shrinking dimensions because of the things like using the mask technologies that we're using, where we're doing optical proximity correction of the masks, they have caused many side effects that create many more design rules, and things have gotten much tougher in actually drawing your different layers because of these design rules.